Welcome back to The Explainer. You ever open a bottle of, say, nail polish remover and get hit with that strong smell instantly? But a bottle of water? Nothing. Well, there's a reason for that, and it's all happening in an invisible world of pressure right above the liquid. Today, we're going to dive into the secret life of mixed liquids and figure out exactly what's going on.
So to really get this, we have to start with something you already know, something we've all seen: evaporation. You know, when a puddle dries up on a sunny day? That's our starting point. It's the first piece of the puzzle.
All right, before we start mixing things together, we've got to understand how just one liquid behaves on its own. So let's zoom way in, right down to the molecular level, and see what's really happening.
Okay, so picture the surface of a liquid. It's a bustling crowd of molecules. But some of them, the ones with a little extra energy, are like tiny escape artists. They get just enough of a kick to break free from the others and leap out into the air. That's it. That's evaporation.
But here's the thing. It's not a one-way street. For every molecule that escapes, there's another one floating around in the vapor above that might just lose a bit of energy and fall back into the liquid. It's this constant dance, a molecule leaving, a molecule returning. Eventually it settles down, and the number leaving is exactly the same as the number coming back. We call this special state dynamic equilibrium.
So, all those escapee molecules in the vapor, they're bumping around, creating pressure. And the pressure they create at that perfect point of equilibrium, well, that's what we call vapor pressure. Think of it like a liquid's unique fingerprint. Every liquid has one.
So what makes that fingerprint different for different liquids? It really boils down to two main things. First, how much the molecules like to stick together. If they have really strong bonds, they're all holding on tight, and it's tough for any to escape. That means a low vapor pressure. And the second thing, temperature. When you heat a liquid up, you're basically giving those molecules a ton of energy, making it way easier for them to break free. So higher temp, higher vapor pressure. Makes sense, right?
And this is the really crucial point to get. There's this inverse relationship. A liquid with a high vapor pressure, one that evaporates really easily, we call that volatile. And because its molecules are already halfway out the door, you don't need to add nearly as much heat to get it to boil.
Okay, so we've got the basics for a single liquid. But what happens when we take two different liquids, each with its own personal vapor pressure, and mix them together? How in the world do we predict what the new pressure is going to be?
Well, lucky for us, a French chemist back in the 1800s named François-Marie Raoult figured out a surprisingly simple rule for this. He discovered that each liquid's contribution to the total pressure is directly related to its mole fraction, which is really just a sciencey way of saying how much of it is in the mix.
Now let's dig into the actual mechanics of Raoult's law. Yeah, we're going to look at an equation, but don't worry, it looks a little intimidating, but the idea behind it is actually super simple and logical. At its core, it's just this. The more of liquid A you have in your solution, the more its vapor is going to contribute to the total pressure above it. It's a straight-up proportional relationship. More of A, more pressure from A.
Okay, you're going to see this symbol, a P with a little circle above it, sometimes called a knot. When you see that, just think of it as the baseline. It's the vapor pressure of that liquid when it's completely pure all by itself. It's its full maximum pressure potential.
So building the full equation is just a simple three-step process. Seriously. First, you figure out the partial pressure for liquid A. You just take its pure pressure and multiply it by how much of it is in the mix. Then you do the exact same thing for liquid B. And for the last step, you just add them together. That's it. That gives you the total pressure of your solution.
And there you have it. That's the whole thing. This one beautiful formula lets us predict the total vapor pressure of what we call an ideal solution. And we'll talk more about what ideal means in a minute. But yeah, all you need to know is what's in your mix and how much of each.
Now, an equation is great and all, but sometimes a picture really is worth 1,000 words. Let's see what Raoult's law actually looks like when we plot it out on a graph. It makes everything so much clearer.
And what's so cool about this is that Raoult's law is a linear equation. You might remember y equals mx plus c from math class. It means that if we plot the total pressure against the composition of our mixture, we should get a perfect straight line.
This graph just lays it all out perfectly. So on the bottom, you have the composition, going from 100% liquid B on the left to 100% liquid A on the right. That first line shows A's contribution growing as we add more of it. At the same time, the second line shows B's contribution shrinking. But the most important one is that top line, the total pressure. It's just a straight line connecting the pure pressure of B to the pure pressure of A. You can find the total pressure of any possible mix just by looking at that line. Now here's where things get really interesting. The mixture of gases, the vapor that's hovering above the liquid, it doesn't have the same composition as the liquid itself. Think about it. The more volatile liquid, the one with the higher vapor pressure, escapes more easily. So the vapor is always going to be richer in that more volatile stuff. This one simple fact is the entire reason distillation works.
So, why do we care about any of this outside of a chemistry class? Because this law, and more importantly, the times when this law doesn't work, explains everything from how we refine gasoline to how distilleries make whiskey.
Remember how I kept saying ideal solution? Well, that's when the molecules of A and B don't really care about each other. They mix, but don't interact much. But in the real world, that's pretty rare. Sometimes when you mix A and B, the new attractions are weaker than the old ones. This makes it even easier for molecules to escape, and you get a higher pressure than you'd expect. We call that a positive deviation. Or the opposite can happen. The new mixture can have super strong attractions, locking the molecules down and causing a lower pressure than predicted. That's a negative deviation.
Now, if you get some really extreme deviations from the ideal, you can create something wild called an azeotrope. It's this special kind of bizarre mixture that basically pretends to be a pure substance. Its vapor has the exact same composition as the liquid. And this weird property creates a massive headache for chemists. The whole point of distillation is that the vapor is different from the liquid, allowing you to separate them. But if the vapor and the liquid are identical twins, well, simple distillation is completely useless. This is exactly the problem with trying to make 100% pure ethanol from a fermented mixture. You get stuck at about 95% because it forms an azeotrope with water.
This strange behavior, which is born right out of the simple laws of vapor pressure, is a huge challenge in the chemical industry. And it leaves us with a pretty cool question to think about. If a mixture can perfectly disguise itself as a single pure substance, how on earth do you break that illusion?